So it's a great pleasure to introduce René Mboro from University of Miami, who's going to tell us about some remarks on Lagrangian submanifolds. René?
Thank you for the invitation. So we have had some lecture on Hyper-Kähler manifolds, and then we'll be interested in this talk on a particular subvariety of them, that are Lagrangian submanifolds. I recall the definition of Hyper-Kähler. Compact Kähler manifold Y is Hyper-Kähler if it is simply connected. If it is simply connected and the space of holomorphic form is one-dimensional and generated by a symplectic form everywhere non-generated. And a Lagrangian subvariety of set is a complex subvariety, submanifold, sorry. So I should have said the dimension is 2n, complex submanifold of dimension n, and such that the restriction of the holomorphic of the symplectic form is 0. So some easy examples of those objects. So in dimension 2, as we have seen the talk of Claire Voisin, there is only one family of Hyper-Kähler manifolds, namely the K-free surfaces, and the curves for dimension reason, because a symplectic form has to vanish on a one-dimensional subspace. Any curve on the K-free is a Lagrangian. Submanifold. And the second example, we recall a theorem that appeared in the talk of Claire Voisin also, due to Matsushita. Was saying that if we have a surjective holomorphic map from an Hyper-Kähler twinfold, with the base positive dimensional, but strictly less than the dimension of y. So a real, you have some positive dimensional fiber. Then one thing was that the dimension of B has to be the dimension. Another thing is that the fibers are complex tori. The general fiber. And another thing is that the fibers are Lagrangian. And also the map is flat, and so. But I'm interested in those two, meaning the sense that to say that just complex tori are other example, natural example of Lagrangian submanifold, and they are particularly interesting because when people study Hyper-Kähler, they are many times interested in Lagrangian fibration and so on. So the goal of the talk of today is to kind of convey or try to convince you that those two should be thought as a model for the rest, not all, but most of the Lagrangian submanifolds of general Hyper-Kähler. So in the sense that the general Lagrangian submanifolds should share a lot of property with those two kind of objects. So there are properties that have been known for quite some time and that can fit into this proposal. So I will call some classical results. So the first result, so I just recall that the general K3 in the moduli space is not projective. It's just is not algebraic, but of course any curve on it is algebraic. For example, you can have elliptic K3 that are not algebraic, but so its Lagrangian are always algebraic. And we have the same phenomenon for general Lagrangian proposition. It is found in the paper of Campana, but he attributes it to Claire Voisin. So let X a Lagrangian. The manifold.
Could you maybe write a little larger?
Okay. Then X is projective, even if Y projective. And the reason is very simple, just a sketch of the proof, is that we have the morphism of odd structure given by the restriction, and the H20 part is contained in the kernel of this morphism, which means that the image, for example, if I take real coefficients, if to see that something is projective, we can use, for example, the Kodaira embedding theorem. So we want to find a rational rational Kähler class. So we have that. We have this. And looking at the cone of Kähler classes in Y, and using that, so H2 with Q coefficient is dense in H2 with R coefficient, of course, we can find rational class whose restriction and the Kähler class whose restriction coincide. So giving a rational Kähler class on X and Kodaira embedding tells us that it is projective. So another result that has been known for some time is that so in the case of curves, the deformation are obviously non-obstructed. The Hilbert scheme is just some projective space. And here also the deformation of the smooth fiber are non-obstructed. It's just an open set of the base of the fibration. And there is another theorem also due to Voisin that say that the deformation of Lagrangian subvariety inside the fixed scalar, Hyper-Kähler, are unobstructed. It means that the Hilbert scheme component that I denote like this is smooth of the right dimension, so dimension h at x. So we see that with those two results fit into this kind of proposal, and I will add two more. First, let me write an expectation, and I will write the result that has been proven. So for curve on K3, we have P1, which doesn't move in a K3 because the K3 is not ruled, and P1 has obviously Euler characteristic, positive Euler characteristic, and for every curve, every other curve, they move, they fill the K3, and they have non-positive Euler characteristic. So the expectation is that let x Lagrangian whose deformation cover or field y. I mean that by that I mean that the obvious thing that if I look at the universal family and the projection to y, this map is dominant. Then the topological Euler characteristic should be of a given sign. Unfortunately, I don't know how to prove it. But what is true is that in the case of a surface in Hyper-Kähler fourfold, we have the following Lagrangian surface. Whose deformation field over y, then you have a kind of alternative. So either there is a curve it can have many components, a priori reducible, contained in any deformation of S inside, right? So I think this case should, I mean, this means that when we look at the Hilbert component and take two members of inside, the intersection contains always this curve. It's a bit strange. I mean, I think it should not exist, but unfortunately, I'm not able to rule out this case. Or we have what we want. The topological Euler characteristic is non-negative. and it is 0 when two general or two members of the Hilbert scheme do not intersect. The second property that I want to bring is the following. It's again for just Lagrangian surfaces. Whose deformation cover Y. Then S has maximal albanese dimension 2. Just like to complex tori has maximal albanese dimension, and curves also has maximal albanese dimension. So before going to sketch the proof of this, I'd like just to give more example of Lagrangian submanifold, just not to give the impression that they are so that's restricted. The class is so restricted. So second series of examples. So let me take S, a quartic, so K3. I can look at sorry, I can look inside the Hilbert scheme of length 2 subscheme of S. I can look at those that are lying on the line. Give me an embedding of Submanian inside this. So this has middle dimension and has so is Lagrangian, since there is no two form on the Submanian, the rational variety. Another example, if I take sigma to be an Enriquez surface, and if I denote its universal cover like this, then S3, sorry, is a K3, and we have an embedding of sigma inside S2, just given by taking the fiber. So it is Lagrangian, again, because there is no two form on the Enriquez. So there are series of, so we can always compute the, express the holomorphic form on the Hilbert scheme of K3 in terms of the holomorphic form on the K3, and this allows us to check that an explicitly given submanifold is Lagrangian. So using that, we see that if we take C to be a curve in the K3, then the symmetric product of the curve are Lagrangian in the Hilbert scheme. So if we take the same curve like this, then we can see using the description that the projectivization of the restriction of the tangent bundle of the surface is Lagrangian in S2. And so we can continue this kind of thing if we take two curves inside the K3, then the blow up of the product is Lagrangian in S2. Maybe more interesting, if we take Y to be the change of notation cubic fourfold, then by work of Beauville and Donaghy, we know that the variety of line is a Hyper-Kähler. Like this, the variety of line. The Hyper-Kähler fourfold. And the remark was that if we take a general hyperplane section, a smooth hyperplane section, so XB, a smooth hyperplane section, cubic threefold, then the variety of lines on the cubic threefold is Lagrangian. Inside the variety of lines of a cubic fourfold. And we can give more examples. We can do the same here using twisted cubics because there is a Hyper-Kähler eightfold constructed by Len and Van Straten, which is birational to the space of twisted cubic on the cubic fourfold, and then it is by work of Galkin and Sovdatenkov, the twisted cubic on the cubic threefold then will be Lagrangian fourfold inside the eightfold. So this was just to give us some example to say that there is a variety of folds. So now concerning the expectation and the question that unfortunately erased. No. In that case, surface has no H1, particularly it doesn't move. No. It is fixed. It doesn't default. Yes. Nice question. I mean, that's nice. I mean, to bring me to something that I should. Another way to say that the subvariety is Lagrangian, which is very something that we will use over and over, is to say that there is an isomorphism between the normal bundle and the cotangent bundle. So this is just linear algebra. So if we write the normal bundle sequence here, and we use here the symplectic form to write the isomorphism to the cotangent bundle of Hyper-Kähler, then we have so saying that X is Lagrangian means exactly that when we look at the composition here, we go to 0 because we take a vector. So it gives us a map here. So I will use it many times. So X Lagrangian, then so, and when we see things like this way, for the example you mentioned, you have then this equals to that, and it is H. So it doesn't move. So back to the expectation. So it is a very simple computation. So if we are on the inverse skip component, I take two members and I compute the intersection. Then I can write it as like this because it's just cohomology classes, and then use all kinds of projection formulas and so to get to what I want to have. So I, of course, is injection, and then I use projection formula to get to integral of the top Chan class of the normal bundle. And this I use using again that. Minus dimension of x. So it is very simple. There is nothing original here, but the problem is to evaluate this term. So of course, when it is the intersection of general member, for example, is dimensionally transverse, then this intersection is just a bunch of points, and then it is positive. And if it is empty, it is 0, of course. But when it is not dimensionally transverse, then we can have problems. For example, if I take this example here. So those Lagrangian subvariety move inside the Hyper-Kähler fourfold, but if I so they are all contained in a divisor. I mean, there is an explicit description of these two, which is the blow up along the diagonal of the self product of S, and you have this exceptional divisor that goes isomorphically downstairs, and all those Lagrangian subvariety are contained inside here, and their intersection is non-dimensionally transverse. So if you take C1 and C2, it is easy to see that you get some P1 that are just the projectization of the tangent space at the point of intersection. And also, if you compute the Euler characteristic, so if as soon as the genus is at least 2, then the topological Euler characteristic, if you go through the formula, is the wrong side. So we have to really require that. We cannot do without that. And something, I mean, there is some question which is natural is I would call it general position for their scheme. I don't know if it is true. So the question is the following. If I take things are not necessarily related to Hyper-Kähler. In this case, if I take a subvariety, so let's say both are smooth. Subvariety such that, say, the Hilbert scheme is smooth at the point that we are considering. Is it true that the general members parameterized by, say it is just a component of the universe. General member parameterized by this component meets transversal, I mean, at least dimensionally transversally. True. Oh. X1, X2. General. That are dimensionally transverse. It is very natural to expect, but unfortunately, it seems not so easy to prove. And also, so we have seen that if I have to require that the deformation cover X. Cover Y, sorry. We have seen that you cannot do without this assumption, and it is also easy to construct a family that are not the full Hilbert scheme that for which it is not true. So it should be something really special with the Hilbert scheme component, the whole thing. But I don't know how to prove it. So what is proven is the following. In the case of surfaces, we can go by hand and have a statement. So for assume that the intersection for two members, any members in the Hilbert scheme component is non-dimensionally transverse. So that S X prime is a curve for SS prime. Let's denote the Hilbert scheme component like this. General. Then I can form for a given S, I can form this map. To which goes to the space of effective divisor of a given class. I will say what is the neon-savory class that I'm interested in, but it is the obvious one. Where gamma H neon-savory of S is just the class of this class of those kind of curves inside S. Okay. Then the image of E is a point. So here I took a Hilbert scheme component, and the irreducible is a point. So this is the lemma that we use to in the case of surface to get the alternative that I had. So the point is the one representing the famous curve that should be contained in all the deformation of S. And if we don't have, if we are not in this case, that the intersection is not is then dimensionally transverse, then this is a positive, and then we have the result that we want. So let me. And so the proof of this lemma is really by hands. We really look at the different cases for this for the dimension of this this map, and we argue with variance. There is no. So let me go to the theorem next. So I recall the theorem was saying that no, the general XNY. So it's just the XS inside the fourfold. I don't even know if you need fourfold. It's just surface. Just surface. So I recall the theorem is about the maximum S being of maximal albanese dimension. So S inside Lagrangian of surface. Deformation over Y. Then S has maximal albanese. Dimension. So there is only one case to rule out, is the case of intermediate albanese dimension, albanese dimension 1. So one thing is that having albanese dimension 1 is topological. So it will stay, I mean, it will be observed by under deformation. And 2 is a classical fact, probably due to the Italian school, that says that if for such S, if S has albanese dimension 1, then the albanese admits such a factorization. So the image is a curve which is smooth of genus the obvious odd number of S, and such that the Jacobian of the curve is isomorphic to the albanese surface. So in particular for such surfaces, and every one form vanishes on a divisor. Every one form comes from the curve and vanishes on, which is a divisor, which is some union of some fibers of the albanese fibration. And if we had the hypothesis that S is Lagrangian, then by what we have seen, you get the isomorphism between the normal bundle and the cotangent bundle, which so this translates into any section of the normal bundle vanishes on a divisor, and we since the section of the normal bundle are in relation to one first order deformation, we can see this information as or we can paraphrasing as saying that the S as non-dimensionally transverse intersection, infinitesimal intersection, or intersection with infinitesimal deformation. We can see the zero loci of sections of the normal bundle are infinitesimal intersection with deformation. So we are kind of back to if we think like that, we are back to an infinitesimal version of what we have seen here globally. And the strategy of the proof is exactly to integrate this infinitesimal picture to an actual non-dimensionally transverse intersection. Natural non-dimensionally transverse intersection, or to actual non-dimensionally transverse intersections. And then to conclude by this lemma saying that it will not be possible. So what I mean by the question is something that goes to deformation theory. More precisely, we want to prove that. So what we want to prove is that given a z inside such surface, by such I mean zero locus, of one form. I want to prove that the functor, the deformation functor, the functor of deformation of S fixing Z. So obviously flat over A and for S. So I want to prove that this functor is unobstructed. So obviously this functor is a subfunctor of the local Hilbert functor. So it is represented by a subvariety of the Hilbert scheme, and saying that this functor is unobstructed is the same as saying that this subvariety is smooth. Yes, and then so if we manage to prove that, assuming that since every first order deformation of S gives rise to such a Z, such thing. It will say that, and so we will be able to fill the whole liberty components. We say that any member, or a general, sorry, just on an open set, a general member S prime inside the vertical component, the same as S, will intersect along one such Z. And then, as I said, then we have an actual intersection which is non-dimensionally transverse, and then we can conclude from the first by the lemma, provided we rule out the fact that there could be one curve inside every surface. So this is the strategy. Okay, and then I just review quickly some of the tools that we use that comes from deformation theory to achieve our goal. So to prove that such a deformation factor is unobstructed, so let me call not those rings like this. So it is to proving that it is unobstructed. So this is also classical. H is the same as proving that one can always lift an object along the AN. Is unobstructed. If for each n, this map is surjective. Where the map is induced by the projection from AN to S1 to and usually, I mean, it is not so easy to lift objects like this, and there is this I mean, what I mean is that usually higher order deformation are much more complicated than first order deformation, and in general for first order deformation we can have a nice theory, and there is a technique called T1 lifting principle, whose strategy is to, instead of trying directly to lift things, this arrow, to go through something which looks more like a first order deformation. Is due to sorry, probably due to Kawamata and probably Ran. I'm not so sure should attribute this. So let me introduce those Artinian ring. So this is just AN tensor A1, and so some auxiliary rings, I would say. And okay, and so we have some projection between those rings, +1, -1, and so on. And we also have, more interestingly, the map, the ring plus C algebra homomorphism, like this, given by T goes to T plus epsilon. This is injective. I mean, it will play a role in the rest of the proof. So this being injective, it tells us that at the level of spect, it exhibits the spec of Dn as a dense subset of the spec of An plus 1. So as I said, so going from An to Dn, because of this presentation, I mean, one can guess that it will be a theory that will look a lot like first order deformation. So it will be a kind of easy theory. And then go through, I think I will not state the proper TA1 lifting principle, but basically the strategy is to go, we are in AN, we go to DN instead of going first to AN, and then we work on DN, and then we conclude by a kind of not exactly completely true what I am saying, but we work on DN, and the work of DN through this map will give us, in nice cases, lifting that we are looking for. Yes, let me just state the precise meaning of what I want to say. So let me introduce a notation. So I denote the fiber. So we have a projection of velocity from Dn to An, and I will introduce a notation for the fiber because I will use it in the statement of the proposition. And then the proposition states that for a given n, if for any deformation at the level n plus 1 of our original surface, the map the restriction map at the level of these so if it is surjective, then the map that we want at the level of An is surjective. So if the map is surjective, then so this is what I mean by going through DN and working through the DN. So when I look at the fibers over a special scheme in AN, I do exactly what I as in I was doing a first order deformation. As I said, the object is over AN, and I want to extend it just with this epsilon. So what kind of thing we want to extend? So the thing is that the first order deformation of S n. So Sn is then the deformation of S over An already, fixing Z are in 1-1 correspondence. Not the first order, sorry. Deformation. Deformation 2 over to go from An to Dn, fixing Dn are in one correspondence with this. As expected, as in the case of first order deformation, it's easy to prove just by co-cycle computations. And this is because we assume S to be Lagrangian, then we get this. And minus C. And because, so this is Sn Lagrangian. And the second step is albanese fibration. Is that we get that this is pullback. So I forgot to introduce notation. So let me denote like this. So up to taking an étal cover of an open subset of the hyperseed component that I'm interested in, I can have the albanese fibration in family. So so we have the notation comes from. So we get that. So as we have first order deformation, if we want to continue our process of deforming, we want to make sure that this is non-zero. And at each step, because if at some step this goes to zero, then we cannot deform. So one lemma is that for deformation fixing for S prime deformation of S fixing Z, OS prime of Z comes from the fibration. The albanese fibration. In particular, it can be expressed as the pullback of a line bundle that has to have, because of the way we chose Z, that has to have the same degree as the canonical bundle of the curve. So for such line bundle, there is just an alternative. Either the line bundle is not the canonical bundle, which is equivalent to the section just such as we want here. So the section B as dual is 0. It is also equivalent to the number of sections of LZ is 1 less number of sections of the canonical bundle, or it is a canonical bundle. So in fact, what we want to make sure is that at each step, this is a canonical bundle, and this lemma of this classical thing of curve tells us that the difference between the two bundles can be detected by the number of sections. and in the T1 lifting, this whole thing of deformation, we will actually just prove that at each time we can extend all the sections to the next step. And for that, so yes, in the remaining two minutes, just quickly say that there is a nice theory of extension of line bundle and sections to the first order at least. But as I've tried to stress, the going from AN to I erased what was AN and DN. Going from AN to DN is a lot like first order deformation. So this whole theory of deformation of line bundles and section can be rewritten to fit our setup, the deformation from object on AN to object on DN. And this is what we do to copy the proof. And then we have to, so there is a, the obstruction to lift section is computable. And then we introduce all kind of object and do cycle computation. And then we prove that the obstruction vanish. Goes.
Questions?
I can ask a question, but I might have missed something up here. But how do you know when the albanese dimension is positive?
Because
sometimes, and is there a way of knowing?
Because my assumption is that the deformation cover Y. So in particular, I have because of an obstruction of deformation, we have the dimension of the liberty component is at least 2. And this is the same as.
Okay. Oh, that's nice. Okay, fine.
Other questions? All right. Thank you very much, René. So we'll proceed with the last talk of the conference in 30 minutes. Thank you.